Yes, let me start by thanking the organizer and, of course, primarily Felix for inviting me and for bringing such a diverse crowd here. So I'm looking forward to maybe discussions one doesn't have every day otherwise. So talking about the theme of geometry and quantum geometry, I'll be firmly in the quantum camp for my talk. And yeah, so the title is already up here. And what I'll be talking to you about is a way of quantum field theoretically approaching this topic by putting quantum gravity on the lattice. Okay. Now, I'm the first person to talk here. Well, I wasn't here yesterday, so I'm not completely sure about quantum gravity. So let me just introduce a few basics by way of introduction here. So we are still looking for a quantum theory that, a fundamental quantum theory that underlies Einstein's theory of general relativity, and that should describe space-time, or perhaps it should be even a unified theory of space-time and matter, which also unifies the principle on the one hand of quantum theory and of general relativity. And that's not just qualitative, but quantitative. So it produces numbers, as I hear say. So where we can pinpoint where kind of the root of our problem lies in addressing this theory, one could say it lies in the fact that standard perturbative methods based on a split, a linearized split, which you already saw on the previous slides of Felix's, where I decompose a general Lorentzian metric G mu nu into a flat Minkowski piece plus a linear perturbation, that doesn't lead to a renormalizable theory perturbatively. And of course, there are old results, so this has been known for a very long time. And then there are two routes. Then the point is there's no one canonical route to follow from there on if your standard method doesn't work. So you can either, you say, okay, we need to go beyond perturbation theories, and the question arises how you do this, or you need a kind of a radically new idea, and then of course, a Pandora's box opens. And I would say that's the moment that quantum gravity lost its innocence, in the sense that it led to a birth of a whole variety of different so-called approaches, where one tries to construct quantum gravity, usually invoking what I call extraneous ingredients. So beyond adding degrees of freedom and symmetries beyond those of the classical theory, and also going beyond quantum field theoretic principles. So if, for instance, if you base yourself on excitations that in some way are extended, this could be strings or loops or what have you, you will typically go beyond the framework of standard quantum field theory. This has led to many decades of people following these various approaches, I would say largely detached from physical phenomenology, and that bears, of course, a risk that you go off on tangents. And nevertheless, or maybe because of the richness of all these approaches, there are long wish lists of questions. So if you add them all up, there's this interesting book that Jay Armas, my colleague from the University of Amsterdam, has compiled. It contains 30+ interviews of researchers in quantum gravity, among them also myself. And Jay made the effort of extracting from all of these chapters what people wished quantum gravity should solve, and he arrived at a long list of a couple of densely filled A4 pages of all the questions that those people wish quantum gravity to answer. So if you see that, you will say, well, clearly these wishes cannot all be simultaneously fulfilled. So this is really highly unrealistic. And indeed, that's also where my talk will go as part of the conclusions I'll draw. So what I want to say here, also putting back an emphasis on geometry, one of the things I think is one problem arises because people do take the notion of quantum space-time often, sort of as some kind of quantum space-time foam, not seriously enough. Okay, so of course you see when you Google quantum space-time foam, you see a picture like this one here presented on the left. So where you imagine you're zooming in, you're just thinking of a piece of empty space-time, which under normal circumstances at everyday scales just looks like a piece of structureless nothing, really. Then you zoom in with your imaginary microscope, and after a while you see, when you come to really small scales, you see quantum fluctuations of that space-time itself appearing, and then when you get all the way to the Planck regime, then, well, it's this undefined quantum foam. Yeah, so this to be understood, highly non-classical regime. So here, really, one can pinpoint the big difference with other quantum field theories. Yeah, of course, that there are big quantum fluctuations, and for instance, if in a theory like QCD, that the vacuum has a not at all trivial structure, that's familiar, but space-time is left untouched. Now, here, the difference is that space-time itself becomes a subject of quantum fluctuations, and that is a totally different situation. So if you take such a regime seriously, as many people do, or at least endorse it, kind of, morally speaking, then you should realize that this is a regime, as kind of this drawing there implies, where you have no coordinate system, no meaningful coordinate system you can use, no meaningful tensor calculus you can use, and standard GR tools are simply not applicable. So the question is, can we compute anything? And how should we do this? Theoretical physics is more than just drawing artistic impressions of quantum space-time foam. So we certainly want to move beyond that. And one other big question is, beyond describing such a regime quantitatively, how on earth are we going to get, the nice, smooth spacetimes of classical GR back from such a thing? How can they possibly emerge from such a foam? So also I want to encourage you to think the theory from kind of from the far end and ask, okay, now what is this theory of quantum gravity going to be in the best of all cases? It's presumably it's very strongly interacting, it's non-perturbative, it's a four-dimensional quantum field theory, in the best of all cases of dynamical spacetime. So our best currently available technical tools and kind of conceptual tools, what kind of inroads can they possibly make? Yeah, what kind of theory is that possible? Can that possibly be? And what kind of information are we likely to be able to extract? As I said, with the best of our tools, also computationally. Now, what hampers us, obviously, is the lack of any phenomenological guidance from either experiment or observation. And that's, again, a problem because, one needs reality checks to keep one honest and also provide, some kind of input into theory construction. So unfortunately, these things are largely absent. So let me, by way of summarizing what I'm going to say, highlight some main messages that come out of my way of thinking about quantum gravity. And that's to, first of all, say, okay, we have found a way to put the theory on a lattice in 4 dimensions, and it's basically addressing the gravitational path integral. So I will tell you that I have a method to genuinely compute that in a reliable way in a certain length regime. And it will give us a tool to really tackle quantitatively the theory beyond perturbation theory. So it's nice in the sense that it brings us back into the fold of quantum field theory without invoking any extra ingredients, which of course are also, as I said, open a Pandora's box in terms of non-uniqueness typically. So, so we can do simulations, numerical simulations, Monte Carlo simulations in a certain regime. And from this already emerge 2 things. So there is a blueprint really, or some non-trivial evidence that this can actually give rise on kind of sufficiently coarse-grained or large scales to something that an object, a quantum space-time that resembles things we know from the classical theory. So that's beautiful. And secondly, of course, it gives us an idea of what this quantum space-time foam might be all about. And at the same time, I would claim it gives us a more realistic picture of what we may hope to be able to achieve in such a theory, going back to a point I have already mentioned. So one way to see these computational methods I'm invoking is also to say, well, I can think of them as numerical experiments. So my theory, you know, my theory is what my theory is, but it's too complicated for me looking at the theory to extract predictions from it in an analytic way, but I have numerical tools that do that for me. Yeah? And then invoking these, using these, I will get to, you know, some kind of predictions, which I then, my hope in the end, may hope to be able to compare to actual phenomenology. And the closest one can get here is, as I would argue, is something that says things about maybe the very early universe, so kind of cosmological applications. So what is the key to all this? Well, one has to define diffeomorphism invariant observables, and that's a theme and a challenge that's familiar from many approaches. In terms of the underlying mathematics, it turns out, surprisingly, that Riemannian geometry or pseudo-Riemannian geometry is not quite enough in this quantum context. So we go beyond that and we work with metric spaces, so where we have notions of distance and we do have notions of volume available, which, however, are non-smooth. They are continuous but non-smooth. And there is no G mu nu anywhere, and there's no G mu nu hat anywhere. And as I would argue, that's a feature. Okay, so after this small introduction, let me now take you to the world of lattice quantum field theory. Yeah, so lattice regularization of the path integral, the Feynman path integral, is really the go-to methodology if you want to analyze a relativistic quantum field theory non-perturbatively. Yeah? Emulating, of course, the most prominent example being lattice QCD. So let me remind you about the general strategy one chooses here. So one, instead of a smooth space-time continuum, you substitute this by a typically hypercubic space-time lattice. Yeah? And the fields of your theory live on that lattice. Why does that help? Well, there is a UV cutoff, in the form of a in the form of a lattice spacing, so-called, which makes, well, if you're lucky, makes a regularized path integral finite. And in the end, of course, you want to take a limit as a goes to 0, a so-called continuum limit. But taking a to 0 is not enough. You usually have to fine-tune your bare coupling constants, typically in the vicinity of a second-order phase transition, to regain or to gain a genuine continuum quantum field theory. So this is not fundamental discreteness. This is not postulating, the world consists of, little bits of a hypercubic lattice, but it's just a tool. And the beautiful thing is this notion of universality, namely that if you take an appropriate continuum and scaling limit, then the system will forget most of the totally arbitrary regularization details you put into this lattice description by just setting it up. So I want to zoom in a little bit on the case of non-abelian gauge theory, and a major breakthrough that helped this methodology take off is the fact is a clever choice of variables, which we are using still today, and which is that of holonomies. So holonomies are variables you associate with the edges or links of a lattice, and they are basically just path-ordered exponentials of the gauge potential along these links. That's the interpretation. So, and they were introduced by Kenneth Wilson in this famous paper very long ago I'm citing here. So what is the beauty of these variables? The beauty is that there is exact local gauge symmetry preserved in this lattice formulation. Namely, these objects UL, they still, they transform non-trivially at their endpoints, but there is very easy ways by, sticking these together to come up with exact quantities. So, and so the gauge group action is still there, but you have it under full control and it's exact. Why is this remarkable? Because oftentimes when we regularize a quantum field theory, symmetries we love and which are kind of essential to the continuum theory are destroyed. So this is not the case here. And this is a very important feature of this formulation. Looking more broadly speaking, if in quantum gravity using lattices, we would only come a fraction of what has been already possible in lattice QCD, we would be extremely happy. In lattice QCD, people nowadays can compute, part of spectra, which then you can almost, straightforwardly compare to data, coming out of particle accelerators. So if we were in that situation in quantum gravity, we should count ourselves extremely happy. Now, it's not exactly a new idea to put gravity on a lattice, quantum gravity on a lattice. So there is what I would call lattice quantum gravity 1.0. So here, as a reminder, I'm just putting the gravitational path integral. So that's kind of the key dynamical object we want to understand. That's what we put on the lattice. So this is pure gravity without matter coupling here. And you see this is kind of a formal integral or sum or whatever over geometries, where by a geometry I mean a diffeomorphism equivalence class of Lorentzian metrics. And I integrate with some to be specified measure over e to the I s, and where s is your favorite gravitational action. So it was very natural for people in the late 1970s and 1980s to really think about lattice QCD as being the example one would try and emulate. So I've taken here a quote. So the very first paper where this is laid out is by Lee Smolin from 1979, where remarkably he was still a graduate student at Harvard. So it's his first paper, and I went to reread it because very recently we celebrated Lee's 70th birthday. And I want to quote from the introduction of this paper, because it has a very prescient statement he makes there. So when one begins to think about formulating general relativity on a lattice, one runs into an immediate conceptual difficulty. In general relativity, the geometry of space-time itself is dynamical and subject to quantum fluctuations. And that's my highlight. It is difficult to imagine how to make a lattice theory in which the lattice structure itself is dynamical. Very well observed, I'd say. At the time, no one really knew how to do it. So the way he and others progressed is by simply working with rigid cubic lattices and basically closing the eye to this contradiction there. And typically in so-called first-order formulations, where there is a connection floating around, namely either Levi-Civita or a spin connection, put these on the lattice and try to see what came out. Unfortunately, nothing interesting ever came out. Now, why was this? Well, there are zillions of problems which I could go into, but I mentioned just a few of them. Well, you have, you have a Vierbein and connections, but your gauge group to start with is non-compact. So that is already the first stumbling block. So all your beautiful integrals using the half measure will simply diverge. Yeah? Same true for the Vierbein. People then compactify these things, but this is a completely uncontrolled thing. Well, how do you equitate? This is perhaps a related question. Then there's a formal divergence, namely that the gravitational action is unbounded below. And the big elephant in the room, well, what has happened to diffeomorphism symmetry? Yeah, because you just brutally put it all on a rigid lattice. So more than very many good reasons of why this never led to anything interesting. So can we do better? Of course we can. Otherwise, I wouldn't have prepared the talk the way I have. But it took us a long time to understand how the specific structural features can be reflected in a lattice formulation of gravity. So the first thing to say is, just by putting gravity on the lattice, it doesn't suddenly become an easy theory. Okay? So that one could have that idea, but why should it? I mean, the structure and conceptual issues are still the same. However, the tools we've been able to develop have brought us definitely further. So what are those? So key number one, so I say, I enumerate 3 breakthroughs that had to happen to make it, to bring us into position to use lattice methodology. So the first is really what Smolin foresaw in his 79 paper, namely we are using dynamical and curved instead of rigid hypercubic lattices. Okay, so this is indicated by this little diagram here. So that's kind of a typical QCD lattice. And with us, spacetimes are constructed as dynamical lattices from building blocks, which happen to be, you know, of a triangular nature, but it doesn't really matter. But so here is a building block that is a fundamental building block in 4-dimensional quantum gravity, which is a piece cut out of Minkowski space with certain edge lengths, time-like and space-like edges. And the challenge in regularizing the path integral is to use these fundamental building blocks to assemble piecewise flat curved spacetimes. So then you have a regularized version of that path integral, and then you try and do the summation and try and see whether there's any interesting continuum limit of that. Yeah? So the second breakthrough really is the analog, I would claim, of this wonderful idea of using holonomies in the Young-Mills case. So here, because what we're doing is you're working essentially with equilateral building blocks, so the edge lengths are not varying, there is an immediate kind of analog of diffeomorphism symmetry. So there are no coordinates involved anywhere, but instead of using coordinates to define where you are in your piecewise flat manifold, you use labels. Yeah? You label the individual simplices and their subsimplices, and that's really how you address them in the computer. Of course, you have to set things up in a way that ultimately nothing depends on this labeling. So what is the nice thing? Labeling things is a very well-controlled procedure, which is very easily taken care of, for example, in these computer simulations we are running. So here we have really an exact symmetry we can deal with in a wonderful way to describe basically pure geometry. So without any coordinate redundancies. So, and very lastly, which is also a very important point, well, the Wick rotation. Yeah, in order to be able to evaluate path integrals, what we do in standard QFT is we Wick rotate them to a Euclidean regime where they become real partition functions, and then we are able to put them on the lattice. In gravity in the continuum, we have no idea what a Wick rotation is. So the typical thing would be to say, well, we don't know that, but let's just start in Euclidean quantum gravity to start, you know, as a starting point, which is physically a totally different thing and a priori in no way related. Now, what the framework I've been working in is a Wick rotation, which is defined on these piecewise flat curved manifolds. And so what you do, you start with a Lorentzian path integral. There's a well-defined map to map it to something Euclidean. Then you do your simulations in that regime, and then you try and, you know, rotate back or interpret your Euclidean computations in terms of Lorentzian physics. So that's, again, progress. So this is a threefold progress. And, well, this was, of course, we are asked to not make this very technical. So here is, however, just to give you a flavor, the flavor of what this is, I've written down. Now, the well-defined regularized version of the path integral for gravity, so the sum over histories here on the left. So it becomes a sum over inequivalent kind of triangulations with a causal structure that emphasizes the Lorentzian as opposed to Euclidean character of these things, where here we have a regularized version of the Einstein-Hilbert action, and this is just to highlight. It has a very simple form with kind of bare coupling constants here, and well, it depends on so-called counting variables. Well, if you want details, ask me about this later. But you know, just to flash this as the object we are putting into our simulations to understand not just the path integral, but also, of course, observables. I'll get to that in a second. So then the task is, are there interesting continuum limits? You know, when we send the lattice spacing, so the sizes of the building blocks, when we send those to 0, and simultaneously send the number of building blocks to infinity, while keeping a certain physical volume, 4-dimensional volume, constant. Two side remarks. The insisting on a kind of well-defined, kind of basically a discrete analog of global hyperbolicity for the spacetimes that go into the path integral turns out to change the universality class compared to purely Euclidean models. So it's kind of an essential ingredient, this causal structure. which I think is a physically very satisfying thing to be able to say. Another side remark is that there's a transfer matrix that's behind this formalism, and one can show that it's reflection positive. And the important physical implication is that if there is an interesting continuum limit, if one can show this, that is almost guaranteed to be unitary. Okay, now, so as I said, the name of the game is to evaluate this object in a limit of large triangulations and small lattice spacings. And that's what we've done with Monte Carlo methods after recrotating, so to make everything real. And then we are able to discuss the convergence properties of these objects. And what we find is a very non-trivial phase diagram. Phase diagram, to remind you, in a statistical system, which this has now become, is to understand how, as a function of the bare coupling constants, which are just the constant you can provide, you can tune, it's these objects up there, the kappa naught, kappa 4, and delta, to understand how the system behaves in this non-perturbative regime you're investigating. And you do find that it does depend, so essentially the kappa 4, which is more or less the cosmological constant, is kind of fine-tuned to its critical value. And then what's left over are two other bare coupling constants, the bare inverse Newton constant, and something that's called the asymmetry parameter. And we find a very non-trivial phase diagram with phase transitions. And note number 1, it's the first time in a 4-dimensional model that we have found candidates for second-order phase transition. And we have good numerical evidence there of higher order. So these are prime candidates for defining a well-defined continuum theory. So we have 4 phases. Phase A and B don't seem physical at all. Phase CDS is a so-called de Sitter phase, where most of our investigations have been made, because it looks the one that has aspects of a well-defined classical limit to it. So to make a bridge with another quantum field theoretic way of trying to understand quantum gravity beyond perturbation theory, there is this methodology using functional renormalization group methods, and they work under the conjecture, with the conjecture that quantum gravity is asymptotically safe. That means there are UV fixed points, which means if you run into one of those, they solve the problem of the infinities by the existence of such fixed point, where all physical quantities that potentially, of course, might diverge in a limit of large energies do by virtue of the existence of these fixed points can potentially stay finite. Such a scenario we can, in principle, and there's a lot of work going into try and verify or falsify in an independent way in these lattice formulations. Okay, let me get now to the results after these kind of rather technical preliminaries. So what is the kind of physics we are studying? As I said before, it's all about observables. Okay, so observables are diffeomorphism invariant quantities whose expectation value in kind of the ground state, this construction delivers for you in a non-perturbative ground state, give rise to expectation values of certain quantities. So the basic formula is, of course, this one. I have some diffeomorphism invariant quantum observable, or in our case, it will be labeling invariant, which is very similar. So, and I just stick it into the trace, as people say, okay, after having recrotated. Now, also very well-known thing is that diffeomorphism invariant quantities, being diffeomorphism invariant is a very, very strict requirement, and typically only satisfied by things that are space-time integrals. So in the pure theory. So for example, of course, if you look at R of x, it's just the Ricci scalar at a point x, you don't consider that as an observable simply because kind of pointing to a point x with label x, it doesn't have a diffeomorphism invariant meaning to it. And more, so you cannot even do it when you're doing a sum over an ensemble of geometries, because then you would have to invent a way, to identify the point called x, in all of these different spacetimes. And there is just no meaningful way of doing it. So instead of R of x, however, this is its non-local integral over the whole spacetime manifold is a diffeomorphism invariant quantity. So that's something that we might naturally study in the quantum theory. So I want to emphasize now one thing. Classically, we also often talk about, so there's a difference between coordinate, covariant, coordinate-dependent quantities and genuine observables. Sometimes it leads to confusion, right? Also in the history of GRS has led to famous confusions about what's physics and what's gauge. But in the classical theory, you always have the freedom to just introduce a coordinate system that suits your purposes, okay? And we are usually completely fine with it. This option is not open to us in this very quantum fluctuating regime, because there is nothing that supports tensor calculus. So there's also nothing that supports setting up local frames. Okay? So it's a totally different situation, which is conditioned by the type of physics we find there, or we believe is there. Yeah? So one has to work around this, and one has to use different ways of talking about the physics. And here, something that I call expectation management comes in. Because, you give a talk about quantum gravity, you say, look here, I have a beautiful computational tool. And then people come, with their favorite quantum gravity problem from this list of the many I4 pages and say, okay, then compute this for me, okay? And I say, ooh, this? Well, but this is formulated in a completely, semi-classical way. How am I ever going to realize this in an operationally well-defined manner in this regime? And the problem then starts that the typical questions that people come up with are very classically or semi-classically motivated, and they're formulated in that language also. You can maybe address them in a semi-classical or perturbative approach, but you cannot, as a rule of thumb, address them in this framework. So again, then you could say, oh, well, then I'm not interested in this framework. But this misses the point. The point is, again, this is a feature, not a bug. It's a question that does not make sense also from the point of view of physics to ask in this regime. There are no little freely falling elevators that would enable me to say something about, let's say, the equivalence principle at the Planck scale. Yeah? Do we expect them to exist in any physically meaningful way? I don't think so. So you have to adapt your questions to the framework you are discussing. Yeah? And a priori, working with our so-called intuition, which of course is deeply classical most of the time, will potentially not get us very far. So the breakthrough results for why you should take this approach I'm talking about seriously is kind of the emergence of classical looking features of the spacetime we simulate in the computer. So for instance, if you look at the Hausdorff dimensions, the spectral dimension, or the shape of the universe that comes out here. So that's a shape, that's a kind of Monte Carlo snapshot of the universe. We understand that, we can match on sufficiently large scale their behavior to those of what one would expect for a classical spacetime. So this is very remarkable, because locally, if you look locally under the hood, the space-time really looks like a crazy, quantum foam. It just, if you intelligently, look at certain observable quantities that are associated with kind of large-scale features, that you manage to map them onto something classical looking. So in particular, I want to highlight this is true for the shape of the universe, which is the three-dimensional volume as a kind of function of a proper time notion that lives there, and this behaves to very great accuracy. Its expectation value behaves like that of a classical de Sitter space. So it's a cosine cube. Why is a cosine not a cosh? Because we are working in a equitated framework. Yeah? So this is beautiful, and this is what I call, an aspect of emergence of classicality. However, again, remember the underlying geometry is nothing like, maximally symmetric, nice space-time, but it's very quantum fluctuating still. Nevertheless, that's a very non-trivial result. So this slide is only here to make tangible to you. I have a computational tool, and now that makes quantum gravity into kind of experimental subject where I propose measurements, which are really experiments on this path integral, if you like, and suitable observables. But let me not dwell further on this, and then you have to analyze your data. And say one last thing about, okay, I've been able to make certain statements about large-scale properties of my quantum space-time. Can I also make more fine-grained statements? And of course, that's where it really becomes interesting. And this is very challenging, but we're making really good progress. So the first question you can ask is, well, you suppose that, the sitter candidate, which in the best of all worlds maybe could be a description of the very early universe, where we always use kind of de Sitter-like spaces by assumption. Can we say something about the homogeneity and isotropy of this quantum object you've generated? That turns out to be a highly non-trivial question because you don't have a metric. So you have to invent diffeomorphism invariant measures of homogeneity. So I've done this in a prototype with a student of mine a couple of years ago. Even more interesting are endpoint functions, right? Instead not QFT, we're saying, okay, give me the endpoint functions and I tell you everything about the theory. What is not known to many people is that in the context of dynamical geometry and quantum gravity, there's a well-defined notion of diffeomorphism invariant endpoint functions. And what we are doing currently is we are studying two-point functions. And two-point function of what? Well, these have to be, again, quantities that are well-defined in this very Planckian regime. And we have found a notion of curvature that stays finite. It's a long story in itself, but this is just to say, doing this and sticking this into our diffeomorphism invariant correlators, in 2 dimensions, we find kind of beautiful results, namely there are no correlations whatsoever. Again, this is a longer story. This is this diffeomorphism invariant 2-point function, and well, it's very non-trivial, and it has a lot of extra features which have to be there because it needs to be diffeo-invariant and well defined in this Planckian regime. Okay, let me end. So by summary, so what I've presented to you is what I would call computer-assisted construction of a quantum gravity theory, putting things on the lattice. So it becomes data-driven. Yeah, we are designing experiments. We understand what the results are. We use these to refine our theoretical description of the theory. And I would claim it's not an approach because this just is, the bare bones ingredients, just a path integral, and without any extras. And this may be the primary gateway to this very strongly coupled quantum Planckian regime. It gives us a first idea of what quantum gravity can deliver, which is very much tied to the type of physics which is there. So again, absence of many classically beloved structures you have to live with, you have to work around, you have to understand what they are. So the typical interesting observers you'll be able to extract will probably be some kind of scaling coefficients, like coming from these non-perturbative propagators. Yeah? We understand what cannot emerge, that is a longer story, and what has a chance of emerging. So anyway, it's reality checks on what quantum gravity might be. It's definitely not GR with heads, right? You're just taking structures, from our classical GR books and the equations, they're putting heads on everything, and oops, we have a beautiful quantum theory. That's really not what it is in this very non-perturbative regime. There's new math behind it. I could elaborate more if people ask me. So random geometry and beyond Riemannian geometry, which is studied in pure math, comes in here. There is a clear path to early universe cosmology. So to further probe the de Sitter nature of these things, and in the best of our worlds, we might be able to make predictions for something like 2-point functions. Yeah, because these are very crucial things people study in cosmology all the time. Yeah? Are we able to verify independently the assumptions one makes in early universe cosmology, or maybe falsify them? Well, either would be very nice. But this is the end of my talk, and I thank you very much for your attention.